All right, welcome back, everybody. So today's a Wednesday, so today's a quiz day. So okay, last 20 minutes of today's class will be in-class quiz, which covers Unit 1A. Okay, no, Section 1A. So we are continuing Section 1B lecture today, starting from page 14 of Section 1B 1.9, Section 1.9 dot product. Let's just take a look at it, okay? So let's begin with the question. How can you find the angle between two lines? Let's say you have a line, let's say this is point O, line OA, line OB. Let's say you're given two lines. I want to know the angle. How can you do such as that? Another question. How can you find the components of force parallel and perpendicular to a line? Let's say this vector A is a force vector. This is a point O. This is a point B. You draw point OB, line OB. Now, along the line OB, how much component of force A do you have? And the perpendicular to the line OB, how much component of force A do you have? Such an information. How can you find those kind of things? This is actually probably a dumb question to begin with. You know the answer. What is it? Can you see this? Okay. Something called vector dot product. Okay. Have you ever seen that vector dot product in the past in some other class, such as what class? Physics. Physics. Did you enjoy physics? Oh man, I loved physics. That is, you should love this class too. I don't know what happened. Do you know the alternative name? This is called scalar product. You know why? That's right, because the result you will get will be a scalar result. That's why this is called scalar product of vectors. Let me underline that. Scalar. So the result is always scalar. You know, oftentimes upper division students forget about the fact. And then you're going to construct the equation using vector dot product, vector cross product, you see later. If you do a cross product, the result is a vector result. If you do a dot product, result is a scalar product. So if you're talking about the equation in terms of vector equation, it looks like only one thing is written, but that one thing may not be a single equation. Vector equation means you have a components depending on the space you apply for that equation. So later on, if you take, I don't know, fluid mechanics comes with some equations. Some of the equations come up with a vector form. A vector form equation can be a single line, but could be a three equations in three directions because it's a vector. You have to be very careful about that. So let's begin with dot product. Suppose you have two vectors, vector A and B, concurrent vectors starting or initiating from here. The coordinate origin may be point O. If you take a dot product, this is the meaning of dot product. If you take A dot B of a vector, magnitude A times B, cosine of angle between them, theta. Now be careful, theta should be less than 180 degrees. You can still do a dot product of more than 180 degrees of theta. What happens if you do such a thing, however? If the theta in between is more than 180, what happens? Minus sign comes up, because more than 180 means one of the vector is going this direction, right? If you take a dot product, of course, minus comes up. Minus result comes up, okay? So let's be careful. So we are going to avoid that complication. So we are going to constrain ourselves. The theta is less than 180 to begin with. Okay. So now, result is a scalar. Once again, let me draw underline. This is a scalar result. Okay. Not a vector. Be careful. And then those are the basic arithmetic rows. Something called commutative row. A dot B is equal to B dot A. You can change the order, you can still get the same result. If you multiply scalar to the dot product, of course, you can open up just like arithmetic. Scalar multiplied by vector A, take a dot product of B, or vector A take a dot product against the multiplication of scalar A times vector B, or A dot B comes up in the bracket multiplied by scalar, everything is the same thing. By the way, this and that is essentially commutative row. Anyways, distributive row is, suppose you have A dot times B plus D. You can, of course, open up A dot B plus A dot D, right? Okay. So those are just some basics. You may or may not end up doing these arithmetic in this class. I think you already know that from physics. So remember, Cartesian vector, let's say if A is a Cartesian vector, you have direction X component multiplied by the unit vector plus direction Y component multiplied by unit vector J plus, okay, direction Z component multiplied by K. So those are unit vectors. This is called Cartesian unit vectors. Of course, you know that. Direction X, direction Y, and direction Z. So those are the vectors in direction X. I is a vector, direction X, magnitude is 1. J is a vector in direction Y, magnitude is 1. K is a vector in direction Z, magnitude is 1. Those are Cartesian unit vectors. So if you take those I and J and K unit vectors of Cartesian, take a dot product, what happens is, if you take I dot I, those are the two unit vectors with the magnitude of 1, both direction of X. The result is 1 times 1 times cosine of 0. Cosine of 0 is 1. Result is 1. How about all the other combinations? I and J, X and Y direction is perpendicular, 90 degrees between an angle. So this is going to be 1 times sine 90. Sine 90 is 0. So those are all zeros, right? So, by the way, I dot J is J dot I, stuff like that. But those are all zeros. Okay? Let's move on next page. So, having said that,
why is it sine 90? Isn't,
where? Ah, sorry, this is cosine. Yeah, I realized. Please fix it, cosine 90. Sorry about that. Appreciate. This is typographic error. Okay. Next page. So having said that, you can basically take the actual dot product between two vectors. Vector A, okay, of course, vector A is a Cartesian vector, AXI plus AYJ plus EZK. Yeah. Now vector B, of course, concurrent Cartesian vector BXI plus BYJ plus BZK. Okay, so this is Cartesian vector A and B concurrent. So if you take a dot product, what happens is this dot product against that. So you're going to basically apply arithmetic rows. So AX, BX, I dot I plus AX, BY, I dot J plus AX, BZ, J dot K plus that. And then you know that this is 0, 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 and this is 0. Those are the only one. Those are only ones. So this remains, and that remains. So the result is this. So this is dot product. Okay. So dot product, if you take a two vector dot product, this is the result. This is a scalar. It's no longer vector result. Okay. Now, this is a practical application of dot product for engineering mechanics, such as the homework you are going to work on today. Okay, so let's say you are given a line A prime. So this is a line A prime. You can express this line A prime by finding what is the unit vector lined up with that line. Okay. In order to do that, you probably want to pick up, I don't know, component of this vector A lined up with line A prime, and then turn that vector into a unit vector by dividing by its magnitude. Right? Then you find out unit vector. That unit vector is going to be a vector of magnitude 1, and then direction is in the direction lined up with A prime line. Okay? So question is, if you are given this kind of vector and an angle, you can determine lots of things. A, what is the angle formed between two vectors? Vector, where's B? I don't know. Well, maybe just to draw a line. So let's say this is a vector A, and then vector B. This is the theta. It's the angle in between. I want to know this angle because I know both vectors. If so, simply do this. Theta is equal to inverse cosine of, take a dot product divided by magnitude of both. If the theta is less than 180, this is going to determine theta. Of course, this is a direct application of the product. Suppose if you want the components of a vector A, one is parallel to this line A prime. The other one is perpendicular to this line A prime. You want to know that kind of stuff. So first of all, the component of a vector parallel to a line, so that this vector, this is called A parallel. Okay? So this is a vector A parallel. You can find it. This is the magnitude of this vector. Take a cosine of theta here, multiply by this unit vector. So mathematically speaking, you take a dot product of A against U, multiply by U. This is the vector parallel to this line. Make sense? Okay. So what about magnitude of it? So this is magnitude. Magnitude is obviously the product. Okay. So what about the component of a vector perpendicular to it? So A perpendicular. Huh?
Is that U, the unit vector in direction of A prime?
That's right. This is a U. This is a unit vector in A prime. In other words, you define a line, then you can use this unit vector to specify the direction of that line. Magnitude is 1. Okay, so that's U. The component of this vector A perpendicular to a line, of course, first of all, you have to find out the vector A parallel to begin with. Once you know the vector A parallel, you can determine A perpendicular, which is vector A subtracted vector A subtract A parallel. And then magnitude is, of course, take a square root of vector A's magnitude itself square minus vector A parallel's magnitude square. Take a square root of it. That's magnitude. Or alternatively, you can determine the theta first and magnitude of A perpendicular. Well, parallel perpendicular. This is perpendicular. A perpendicular is A of sine theta. You have a sine. Okay, parallel is cosine. Is that right? Okay, that's magnitude. So magnitude of vector A, one is parallel to, one is perpendicular to. The magnitude can be found either taking cosine or sine. Of course, it's a trigonometry. What I'm talking about, of course, you know that. But one of them is, of course, the product. Okay. So having said that, those are very simple stuff. Let's just start applying those things in class example 191. Okay. So let's just take a look at your note. This is class example 191. Let me just zoom in a little bit more. Determine the angle theta between y-axis of the pole and the wire AB. Can you see the wire AB? It's kind of faint. Let me just redraw wire AB again. So using this kind of. So wire AB is this. This is wire AB. Okay. So typically, if you say line AA prime or wire AB, this is a wire connecting from A to B. By the way, did you get my email yesterday? I realized, hey, I said totally wrong thing in the classroom. I tried to correct it. So let's be careful. So I want to be consistent to that. So this is the wire AB. That means wire originated from A to B. So this is the starting point A. This is the end point B. So this is called wire AB. Okay. Do you want to create a position vector? How do you call that position vector? RAB. Okay. So I think I said the opposite in last class. So let me just correct it today. So I'm going to start with the sketch. So this is the Z, okay? And then looks like this is the pipe. Okay. This is Y. This is X. Okay. So this is X, Y, Z coordinate. Usually it's a good idea to establish that coordinate to begin with. I'm not going to put dimensions because dimensions are already given here in the original figure. So I'm not going to correct my sketch. And looks like location B is given here, around here. Location is B. And then wire AB is given. Okay. So this is A. This is B. So wire AB is defined. And then looks like the angle, okay, angle is angle between wire AB and the Y coordinate. This is theta. This is something I want to know, okay, right? And then this is location C, location A, location B, okay. So first thing, what do you want to do first of all? That's a good idea. So let's just define position vectors. But before you even do that, this is my tendency. I want to share my tendency. It looks like I have to determine position vector representing this line and position vector representing that line. And then looks like what I want is angle between them. So I want to determine two position vectors and take a dot product. It looks like that. So in order to determine position vector, I want to define the position vector based on the coordinate positions. So this is a location C, isn't it? So location C coordinate, let's say CX, CY, CZ. I want to kind of clarify that to begin with. What's that? CX, CY, CZ. Of course, you know, this is coordinate origin 0, 0, 0. That's right. So what about position A, which is AX, AY, AZ? What are those? Let's figure out by looking at the figures here. AX is, what is it? 0. What is AY? 3 feet. AZ? AZ 0. Unit is feet. Okay. How about here? BX, by, bz. Take a look at your note. What is bx? Bx is bx. What's bx? 2? Is that 2? Okay. How about by? Is that also 2? Okay. How about bz?
Wait, on y is would that be 3? As you said 1.
By location here.
Yeah.
What's by?
2? Oh.
2, right? 2, right?
Negative 3 or negative 2.
BZ is negative 2?
Yes.
Do you agree? Everybody agree about that? Please double check. So coordinate position, I want to clarify to begin with because it's going to make me much easier time to find out position vectors. So position vectors, okay, so position vectors, okay. So I want to find out, first of all, RAC. RAC is, let me just use this. Wow. RAC is, it's too thick, but this is too thick. This is RAC. Why is that? Because this is a position vector from A to C. That's why it's called AC. Okay. What about position vector AB? This is RAB. Why is that? Because this is a vector from A to B. So first of all, RAC, what is it? This is going to be found by the following, okay? Important. So RAC is equal to, this is a position vector from A to C. This is going to be given by C minus A, XC minus XA, I plus YC minus YA, J plus ZC minus ZA, K. This is the standard notation. Hopefully, I'm going to employ throughout this semester consistently. That means I'm calling this position vector RAC because this is the position vector from A to C. But however, if you want to find out the vector itself, you have to reverse it, and then C minus A you have to do. C minus A you have to do. C minus A, okay? So what happened? So XC0, YC0. Sorry. What am I doing? Just forget about what you just said. Sorry about that. Sorry. Let me redefine once again. Okay. So this is actually XC, YC, ZC. This is X of C, Y of C, Z of C. Okay. This is XA, YA, ZA. This is X of A, Y of A, Z of A. Okay. And this is XB, YB, ZB. This is X of B, Y of B, Z of B. That's right. Sorry about that. I apologize.
That's the notation you would like us to use.
This is the notation later I use for something else. Sorry about that. Let's just avoid the confusion. So XC is 0, YC is 0, ZC is 0. Those are all zeros. Those are all zeros. XA is 0. The only non-zero component is this. This is 3 foot. ZA, this is 0. So, what is your conclusion? RAC is. What is RAC?
Region.
Negative 3J. foot. So be careful. Because of the definition of position vector, RAC is, of course, in the negative y direction, magnitude 3 minus 3j foot. Make sense? Okay. So that's how I construct the position vector. How about RAB? Position vector AB. This is, once again, position vector from A to B, but in order to find out this, you're going to do this. Flip-flop xb minus xa of I, yb minus ya of j plus zb minus za of k. Okay? And then it's going to be easier time. So xb, this is 2 foot, xa 0. YB, this is 2 foot, YA 3 feet, right? ZB minus 2 feet. ZA, what's Z? 0. Okay, so what is the conclusion? RAB is, what's this? This is going to be 2, right? 2, right? 2 minus 0. So 2i, what's this? 2 minus 3, minus 1. What's this? Minus 2, minus 0, which is minus 2. Do you follow that? So this is the position vector RAB. Okay. So position vector RAB. This is a position vector RAC. So question is, what is the angle between them? How can you find such a thing?
The inverse cosine of the dot product.
That's right. So theta is equal to inverse cosine. Take a dot product, RAC vector, dot product against RAB vector, divided by magnitude of RAC, magnitude of RAB. Well, wait a minute. What are those magnitudes? Let's just find out. Magnitude. Okay. So first of all, what is dot product? Let's do a dot product. This is going to be, do you remember how to do dot product? This is minus sun j minus 3. Sorry, sun is Japanese. Sorry about that. 2i minus j minus 2k. Minus 3j dot product. 2i minus j minus 2k. So this is taking dot product. So dot product really means that let me just do it more thorough manner. This is actually a little too much simplification. So let me just do this, okay? So RAC is 0i minus 3j plus 0k, okay? So this is more complete description of RAC. RAB is 2i minus j minus 2k. So if you take a dot product for those, obviously you do 0 times 2, 0 times 2 plus, you do minus 3 times minus 1, minus 3 times minus 1, okay? Plus, you do 0 times minus 2, right? Now, of course, without thinking, this is 0, this is 0. So the result will be minus 3 times minus 1, so this is 3. So dot product of two vectors RAC dot RAB is 3. This is scalar. Okay, and also magnitude of each vectors. Okay, magnitude of position vector AC. Anybody? What is the magnitude of position vector RAC? Magnitude, I'm talking about. Magnitude. Magnitude is 3, of course. About magnitude of position vector AB. Well, you have to do a math. Of course, take a square root of each component. So component-wise, this is a 2. 2 square plus this is minus 1. Minus 1 square plus this is minus 2. Minus 2 square. So this is going to be 3 again. Okay. Therefore, let's just plug that in. Thus, theta is equal to inverse cosine. The product resulted in 3. Magnitude of RAC is 3. Magnitude of RAB is 3. 3 divided by 9. Take an inverse cosine. What's the angle? Anybody?
70.53.
70.53. Any confirmation? Anybody?
Same thing.
At the same time? Okay, good. Looks like this is the angle. Do you have any question here? So I hope you understood how it goes. So this is the application of dot product to find the angle between two vectors. So first of all, you have to express the line using two position vectors. Suppose if there's a force involved, you are going to find out position vector first and then turn the position vector into unit vector specifying that direction. That unit vector multiplied by the magnitude of the force, that actually creates the force vector. Take a dot product that is going to give you how much portion of the force is acting in this direction. It's a component force in certain given direction. That's something you've been doing for the first homework sets. You can actually solve the same thing using dot product. Okay? All right, so let's move on. Homework 191. This is hot, already assigned. Let's take a look at class example 192. Okay, page 18. Determine the magnitude of the projected component of force. Oh, this is from projected component of force F along the pole. Okay. Okay, so I just really don't like my own solution I did a long time ago. So let's just do a new solution here. So first of all, let me start doing this. I'm going to define position vector. What kind of position vector do you want to define? Because your answer, your desired answer is the forces component projected onto this pole. What kind of position vector you want to find? A to O. So let's find out. Position vector RAO. This is a position vector from A to O. So this is basically XO minus XA. I plus YO minus YA, J plus ZO minus ZA, K. So the position here, okay, XA, YA, ZA. What are those? XA is, anybody? What is XA?
-2.
XA, is it
Oh, you're
negative?
doing- oh,
4 is kind of coming towards you. This much towards you.
so you're looking at 3.
3, isn't it? This is 3. Do you follow? X is 3, and YA, what's YA? YA is negative, isn't it? Y is what? Negative 2. Y is negative. Yeah, that's right. ZA. Z is positive. So that's 6. That's right. So make sure you follow through it. So this is a coordinate position of position A, 3 and minus 2 and 6. Of course, here is coordinate origin, 0, 0, 0. This is XO, YO, ZO, 0, 0, 0. So let's just find out position vector AO. This is 0 minus 3I plus Y0 is 0, okay, 0 plus 2, right? XA is, YA is minus 2, so 0 plus 2. Do you follow? And Z0 is 0, ZA is 6. So 0 minus 6. Do you follow that? So as a result, this is going to be what? Minus 3I plus 2J minus 6K. Unit is feet. Okay, good. Go ahead.
So do you have I had J twice, right? 0 minus 6, right? It's supposed to be K. By the,
Sorry. I oftentimes do that kind of stupid thing. Appreciate that. So this is K, yeah, that's right. Okay, that's right. So next step, let's find out the unit vector. UAO. No, not OA. I'm writing OA by saying AO. Something's wrong here. Unit vector AO. Unit vector AO is, of course, okay, the vector itself, minus 3I plus 2J minus 6K divided by its magnitude, isn't it? So this is okay, this is minus 3 square plus 2 square plus minus 6 square. By the way, minus 3 square plus 2 square plus minus 6 square, take a square root is 7. So this is going to be minus 3 over 7I plus 2 over 7J minus 6 over 7K. Now, unit vector usually don't need a unit. So I skip the feet here because it's unit vector. Okay. So now, projected component. Of force F. So you're going to find out essentially FAO. This is going to be essentially force vector F taken dot product against UAO. So this is force vector is given in the program. So this is minus 20I. Oops, let me just finish. Plus 50J minus 10K. The product against minus 37I plus 27J minus 6 over 7K. If you take the product, you just do it by yourself, you should get negative, what, not negative, you should get the 31.43. The unit is pound. Please do your math, okay? Do your math means, okay, so that means this times that plus this times that plus this times that. It's going to be 31.43. Okay. Any question here? So this is basically, holy cow, the end of 1B, isn't it? That's right. So we completed section 1B today. I'm going to announce the homework and next quiz, but most likely next week, okay? All right. Any question? Let's just stop recording and then let's just do a quiz.